Coulomb's law. Recall that if you have excess protons on an object, it will become positively charged. If you have excess electrons on an object, it will be negatively charged. If you have like charges on two different objects, they will repel, such as positive and positive or negative and negative. And if you have unlike charges, opposite charges, they will attract. That's the law of charge. So reviewing the law of charge some more, recall that opposites attract and likes repel. So in this first example, since we have excess protons on this sphere and excess electrons on this sphere, the charges are opposite and the forces are pulling toward each other. Opposites attract. These two models show likes repelling. If both of these spheres have excess protons and are positively charged, then they want to run away from each other. Likewise, if these two spheres down here have excess electrons, both of them are the same type of charge, then again they would repel and want to move away from each other. So likes repel. We also got a brief glimpse of Coulomb's law. That's the law that tells us how large the force is between charged objects, depending on how big the charges are and how far apart they are. And that's what we're going to dig into and get more specific with right now. This is an illustration of the apparatus that Coulomb used to find his electrostatic law. What you can see here is that we have two different spheres. They're going to represent two different charges, and we have the same thing on this other side of a torsion bar. This torsion bar is free to rotate on this wire, and there's a mirror attached, so a light beam can come and hit the mirror and go out this other side. What happens as the force of attraction or repulsion happen here and here, this will either turn in this direction where they're both attracting, or it'll turn the other way where you get repulsion. And therefore we can measure how much this wire is twisted based on the direction of the laser light, and we can also measure how far apart these spheres are. So that's the apparatus that we'll continue to look at. Let's start off with our relationship between force and charge. We have a case here where we have two charges, Q1 and Q2, and we're going to have a charge of just one general quantity we're going to call 1 here on either one. This one's positive and this one's negative, so they're attracting. To relate this to Coulomb's apparatus, the big Q is going to be our Q1 and the little q is our Q2, and it's just symmetrical here. Notice when we have a relative charge of 1 each, we have a force of 1, a general relationship force of just F. When I double the charge on Q1, I make this twice the charge it was before, and also this twice the charge it was before, make this twice the amount, then we double the force, even though this charge stayed the same. Doubling one of the sphere's charges will double the overall force on both of them. Newton's third law, for every action there's an equal and opposite reaction, comes into play here. Notice it doesn't matter which one we choose to charge. We could keep big Q of a charge of 1 quantity and then make little q a charge of 2, and it'll still double the force on both. If we make big Q 3 times what it was originally and little q still 1, then we notice that this is 3 and this is 1, that the force is increased 3 times. Interesting. And then when we go down and we make both of these, increase them from their original 2 times each, we get 2 times 2 for a quadrupling of the force. So what we can derive from all of this is if we just simply take the relative charge on both and multiply them, 1 times 1 is a force of 1, 2 times 2 doubles, or sorry, 2 times 1 doubles the force, and so forth. 2 times 2 quadruples the force. We get this force and charge relationship. So Coulomb's law says that force is directly proportional to the product of the two charges on the objects. Let's take a look at this simulation to show the relationship between the product of the charges and the force. To start off with here, charge 1, Q1, is roughly 20, and charge 2 is 250, and the force is 2 newtons. If I double the charge on Q1 by making this 40, then we see that the force doubled. If I bring this back to 20 and I double the double the charge on Q2 from 250 to 500, then the force doubles. If I double both, bring this up to 40, then within experimental error calculations here, within significant digits, this goes up 4 times to 8 newtons. You can't really get between those two, 7.9 to 8.1. Anyway, goes up to roughly 8 newtons, or quadrupling, because we doubled both. And changing the type of charge on one of these just makes them repel rather than attract. Now let's take a look at the relationship between force and separation distance. In our diagram here, we're going to keep the charges the same at 1 in all of these cases, but we're going to change the separation distance. Sometimes the separation distance is given a symbol r for radial distance. So we're going to start off with what we're going to call r equals 1. That's like this distance right here we're going to call 1 between Q1 and Q2, and it's identical on this other side. Now what we're going to do is we're going to move this Q so it's twice as far away, and we're going to move this one so that it's twice as far away. And so we've increased the radial distance, we've doubled it. When we do that, what we see is the force actually cuts in 1/4 of what it was before. So it divides by 4. So doubling the distance, keeping the charge the same, reduces the force 4 times. If we triple the distance, move Q out here so that this distance is 3 times as big, and the same thing on this side, what Coulomb found out is when we triple the radial distance, the force is divided by 9 from what it was originally. It's gotten a lot smaller here and here. And so, very interesting relationship. If we look here, we've doubled the radius, the radial distance, and the force went to 1/4. We tripled it and went to 1/9. So if you can follow the pattern here, 2 squared is 4, and 3 squared, or 1 squared is 1, 2 squared is 4, and 3 squared is 9. So, but it's getting smaller. So the way we write that in equation form is we say that the force is proportional to 1 divided by the radius squared. Notice when the radius goes from 1 to 2, 2 squared is 4, the force will have dropped down to 1/4 of what it was. So this is the next part of the relationship of Coulomb's law. We're going to go back to our simulator now. I made both the charged objects positive so that we could see the arrows more clearly since they're repelling. And they are 3 squares apart, from center to center, 3 squares apart. That's the radial distance, r, and the force is 12 newtons. If I double the distance of this one, you can see the force shrinking. 1, 2, 3 squares more right there. You can see that the force has gone from 12 down to 3 newtons. The force has shrunk 4 times. So doubling the distance shrinks the force 4 times. That's the 1 over r squared relationship. Now if I continue and go 3 more, 1, 2, 3 more, then you can see that the original 12 has been divided by 9 because the radius has increased 3 times, and 3 squared is 9. And that is the inverse square relationship of distance and force. You can see the reason for the inverse square law with charge is very similar to the intensity of light coming from a light bulb. As you move out radially, the intensity of light at this location, it's all the light rays going through this square, but if you go out twice as far, you notice that same intensity has to be divided up amongst 4 squares. So doubling the distance reduces the light intensity by 4, and tripling it reduces all of this light has to go through all 9 there. So that's a good visual of why the inverse square law is what it is. And this is the graph of distance versus intensity in this particular case. Now we're going to combine our relationship with charge and force and the separation between charged objects and force. So recall that force was directly proportional to the product of the charges, so that goes in the numerator, and that force was inversely proportional to the separation distance squared. And so the r squared goes in the denominator. And when we do that, we're getting really close to Coulomb's law. But notice it's not quite equal, because when you measure this force and you do this math, it's off by quite a bit, but it's proportionally always the same. So let's see what the missing piece is. When Coulomb was doing his measurements, he kept measuring and using this relationship. He kept being off by the same exact amount. It was proportional, but it was always off by the same number. So he noted that number, and that became the missing link here, the missing piece known as the electrical constant. And so the final touches was taking that number. Whoa, it's a huge number, 9 billion. And it's got a crazy unit here too, Newton's meter squared over Coulomb squared. We'll ignore that for now. 9 billion. So if you multiply the Q's and divide by the r squared, and you multiply by the 9 billion, the equation works out, and we can finally have an equation. Now, 9 billion, that's a huge, huge, huge number. And the reason that's a huge number is even though there are tiny amounts of charge on electrons and protons, if those protons and electrons get close enough and this R gets really tiny here, then this force builds up to a very big force. Electric force is very, very strong. And you can see in steel here when the carbon atoms, the dark ones, are close to the iron atoms and they pack in closely like this. It takes an awful lot of force to break apart steel. In fact, we say that you can't bend steel. And there you have it, Coulomb's law. And Coulomb's law says that the force between two charged objects will increase if either or both of the charges increase. It goes as the product of those charges. It also says that if these charges get further apart, their radial distance increases, then the force will decrease. And it'll decrease significantly because it decreases with the square of the radial distance. And it also says that the force of electricity is pretty strong because this constant K is 9 billion. One way you can think about it is the force of electricity is strong, and the other way you can think about it is these charges are super tiny on electrons and protons, and so this has to be a big number to add up to a significant force. The last thing is the forces in these two cases, the forces are the same amount. The only difference is the direction, because remember that opposites attract and like charges repel. So these are pushing away, these are pulling, but the force, the amount of the forces in both of these cases are the same. And that is Coulomb's law. And Scratch's parting comment? And good luck on your quest for continuous improvement.